So, welcome to the physical chemistry lecture number 7, which is open. Thank you for agreeing to present. We are in the physical chemistry class, which means we want to interpret and predict results of instrumental measurements. And on this way, we need to get through abstract theory of quantum mechanics, which includes some postulates which can be proved. It's just acceptance between community. And the best way, if class attendees present them one-to-one. And then last 3 talks will be a little bit of mathematical background that we all need to refresh before we dive into problem solving. So if you haven't seen, so here is the list of presentations. When you are approaching, please try to speak to the microphone. Better to put it in the pocket and mount, or just carry. The slides are here, so you can just try to click on your. They're numbered by names and number in the order. So try to click, open, enable for presenting, and then go ahead in presenting. So the first presenter is Wyatt Heringer. 4 minutes presentation, 1 minute questions. Questions are encouraged. And for reviewers.
All right, I'm Wyatt, and Postulate 1 was my privilege. Okay, so here's the statement for Postulate 1, but we're going to look at a couple of things specifically that are the most important to highlight. And the first thing is in bold. So all possible information about the system can be derived from the state function. So first we need to talk about measurable properties. Measurable properties are observables. So comparing classical mechanics and quantum mechanics. So classical mechanics, for example, say if you wanted to find the trajectory of an object going through space at a certain point in time, you would need the starting position in space, the starting momentum, and all of the forces acting on that object within the time frame that you're looking at. And so those are all observable and measurable properties that you can find through measuring. And if you know all of those, then you can find the motion through space at a specific point in time. Now, when we look at quantum mechanics, the state or wave function, which is notated by psi of RT, once you know that, you know all of these observables and can calculate anything you need to know. That's the only thing you need, only observable or measurable property that you need to know for this. The second thing we'll look at is in general, n is 3 times the number of particles in the system. And then it notes that it doesn't matter what coordinate system you're using. You can use Cartesian or spherical polar, as long as you just adjust your calculations accordingly to what coordinate system you're using. So the set of spatial coordinates for a particle can vary based on the number of particles and the selection of spatial planes. So this is just saying that typically you'll be working in 3D because you'll be looking at volumes. But depending on if you're looking at a 2D or 1D, the R might be just an X or a Y, and then you'd integrate just within that 2D plane. And then depending on how many particles you have, say if you are in 3D and you're working with 2 particles, you'd have an X1, Y1, Z1, and X2, Y2, Z2. That's all included within the spatial coordinate of R. You don't have 2 separate ones. And an interesting thing, as we talked about a little bit, was the probability density when you integrate over a volume of your function times the complex conjugate. And the probability density is the probability that the particle will be found, the particle of the state function will be found within that volume you integrate over. And as I said before, typically it'll be in 3D, but sometimes if you're working in 2D, then you just adjust the dx, dy, dz. And often that will be notated as d tau. So another property of the probability constant is if you integrate over all space, so from -infinity to infinity, the probability constant needs to equal 1 because within all space, there's a 100% chance of finding it somewhere. Another requirement for wave functions is that the wave function must be normalizable or square integrable, which just means that when you integrate the function squared over all space, it needs to equal a constant that is less than infinity. And that's a requirement to satisfy the probability constant from earlier. That's a requirement. And then another requirement of it is that the wave function must be single valued, continuous, and finite, because if it's not all three of those, then you're going to run into some problems with like realistic, physically it won't be realistic if you don't have those requirements. And for a couple examples, the first one, if you have a wave function that's cosine of x, when you try to normalize it, it's not a constant. It's not less than infinity. So a cosine of x, for example, wouldn't be a wave function that would be suitable. But if you're using, say, e to the negative x, when you integrate that, you'll get a constant, say 1/2, which is less than infinity. So then that would be a suitable wave function that you could actually use. And then there are references. Does anyone have any questions?
Please join me in thanking Wyatt. Questions? It's a chance. I have one. Are there situations when state function doesn't change over time? Can you just make a fantasy or predictions?
Where it doesn't change over time?
Yeah. Situations when it doesn't change over time. And it makes connection to several next talks.
I can't think of one off the top of my head.
So there are some specific state functions which do not like to change over time.
Okay.
And it is what we were talking before, eigenstates. Make sense? Eigenstates are state functions that do not change over time.
Okay.
More questions? If no, please join me thanking Wyatt once again. The next presenter is Cybele, Lemuh, and Njimoh. Please teach me how to pronounce
Lemuh.
Njimoh. Okay, so Lemuh, Njimoh, floor is yours.
So I'm gonna talk about postulate 2. So basically, what postulate 2 says is that for the physical property, there's also in like linear momentum or kinetic energy, there's a particular operator for that in quantum mechanics. So basically, in here, what I'm explaining is that, for example, for like linear momentum, we know that linear momentum symbolizes a speed that equals mass times velocity, and kinetic energy is 1 over 2 mass times velocity squared. And in quantum mechanics, there's an operator which describes those physical properties. So basically, operators, we usually represent operators by an accent. So using a symbol, for example, A, O, U, and an operator is linear for any two functions C or P. When we take the operator times times C plus phi, and that equals the operator times C plus the operator times phi. Sorry, I made a mistake there. Just not easy, but whatever. And where basically A and beta are arbitrary numbers. Multiplication and derivatives are also like examples of operators, but square roots aren't examples of operators, since if we take the square root of C and phi, we can say that equal to the square root of C and plus the square root of phi, because that doesn't make sense. Okay, and then an operator is said to be Hermitian if its complex conjugate equals the with the same number, so basically the complex conjugate of A equals A. And then that's when we say the operator is Hermitian. And basically here I just showed the proof that you take to integrate basically the wave function, or like if you integrate an operator A, basically we get that the value A equals its complex conjugate. And basically why operators are important is that because we scientists have determined, for example, the operator of momentum, and using that we can able to like determine an operator for the kinetic energy. So which here I use, we know that the kinetic energy is 1/2 mass times velocity squared. So which equals to the momentum squared divided by 2 times the mass. Since we know that the operator of momentum, which is basically the derivative of like minus h squared divided by 4 pi squared, we plug it into equation 1, and then we get the operator for the kinetic energy, which is minus h squared divided by 8 pi squared times mass. Okay, and then finally, here is the table of basically operators that are derived from classical expressions. Basically the position, the operator for position symbolized with the accent x. The operator of linear momentum, which shows minus IH, and then the operator of kinetic energy, which we derived it from the momentum previously. And basically there are other operators which you can use and then derive. And I guess that's all.
Okay, please join me in thanking Cybele. So questions? Right now we'll go just quickly for next presentations. I'll design maybe a way to reward anyone who asks questions, because it's a healthy thing. I looked at one. If any of the operators that I need I'm missing in your table, what are the general rules to compose quantum operators?
So basically, as I went, for example, for the kinetic energy, right? I went through and like I knew that kinetic energy basically. I constructed an equation where it has the momentum in it.
Mm-hmm.
I know the operator for momentum, which is given from the table, for example, and then I plugged in. So basically, I know the operator for the momentum, which is this, and then I substituted my momentum into equation 1 and got the operator for kinetic energy. So basically, you just take an operator, a non-operator that you know, and then construct it into the classical mechanic equation.
Okay. Yeah, excellent. Thank you. No more questions. But thank Cybele Njimoh once again. Okay. So our next presenter is special in the sense that she will connect to us via Zoom. So, okay, Mai Ceesay. So you are co-host now. Please share screen.
Okay.
And now we have two important concepts: state function and operators. Now there will be at least 3 presentations on the process of measurements, which is like one needs to connect our abstract thing with real life. So Mai, floor is yours. Please go ahead.
Okay.
And whoever is on Zoom, if possible, enable cameras so that it's easier to read what is spoken by lips, if possible. If not, go ahead.
Okay. Hi, everyone. My name is Mai, and I'll be giving you all a rundown of the third postulate of quantum mechanics. So this postulate states that any measurement of an observable property A will only yield eigenvalues of the quantum mechanical operator A. Key points here are an observable property. A here means anything or some physical property that we can measure. Example, position, momentum, energy, etc. So the postulate is saying that whenever we measure this quantity A, the only value we'll observe are eigenvalues of the corresponding quantum mechanical operator A, here, A with an accent. These set of eigenvalues are going to obey the eigenvalue equation shown here. A quantum mechanical operator A acting on a wave function is going to equal some eigenvalue times the eigenfunction. This is the key for the mathematical representation. A with the accent represent the operator, and that's the wave function or the eigenfunction, and this is the eigenvalue of the operator. A little example so we can understand this better. If we have our total wave function psi equals one of these eigenfunctions here, then we are going to measure A sub I, which will represent the eigenvalue for that specific eigenstate. And it is going to be the only possible value that we can measure in this case. Questions?
Okay, please join me in thanking Mike. Any questions? Questions one? I do have one. The examples of lowercase a sub I. Mai, will you please give an example? What is an observable?
Unobservable?
Example of an observable, not definition. Like,
oh.
What is measured on experiment and then predicted by quantum theory?
Position.
What else?
Momentum, energy.
Okay, so energy, which energy you typically measure on experiments in like physical chemistry? Or you may have heard it in freshman chemistry.
I don't get that, you say?
Which energy are you measuring? You've told energy is an observable.
Yeah.
So give an example of experiment.
I don't quite get that.
So everyone, please think about it and try to give an example. Even I will answer the question right now. Try to make connection when you are speaking. So when one is looking for spectroscopy for energies at which atom or molecule accepts or not accepts energy, they are often discrete, and those transition energies are one of the examples of quantum mechanical observables. Yes. Okay. More questions to Mai? If no, please join me in thanking her once again. So Mai, you can stop sharing. I will share it on this end. Okay. And when anyone is finishing presentation, maybe try to close or send your talk on the background. So next is Joe Dieter, right? So, wow, you have some animations. Yeah, floor is yours, and you continue the story of observables and measurements.
All right, so I have the fourth postulate of quantum mechanics, and the formal definition is word for word: let alpha be some observable whose operator A has a set of eigenfunctions phi sub j with eigenvalues a sub j. If a large number of measurements of alpha are made on a system in the state psi, it's going to be given by the following equation. So the expectation value taken over some thing in space, d tau. This equation is useful for determining expectation values for various quantities like momentum, position, potential, and kinetic energies. and so on and so forth. So to kind of break this down, as I said before, it gives the expectation values of some given measurement in a space, d tau. So it can be either in like Cartesian or polar coordinates. And the operator is given in like a state psi, which in our case is our wave function. An example of an operator could be the Hamiltonian operator that we've discussed in class. And that state phi or psi, excuse me, will have a set of eigenfunctions, again, wave function, which by taking a sufficient number of them over that integral in space, you will have, you'll be able to find the probability of finding said electron in some space. So for example, one form that this equation can take, the expectation is for position. And then this can obviously be, like I said, in Cartesian or polar coordinates. So this could also be y or z or r, theta, phi. You kind of get the point of it, but yeah. So as you take the integral from negative infinity to infinity, the I completely lost my train of thought. I'm sorry. It's known that if we take the integral over all of space, it will equal 1 because there's going to be a 100% chance of finding that in there. However, if you're trying to look for a specific particle in or specific position in space, you have your complex conjugate of the wave function times your position operator, which in this case is just x, and then your wave function over taken with respect to the position. And that's all I got.
Okay, so please join me in thanking Joe. Any questions? Probably you were not thinking about designing questions this time, but for when we will do more presentations, it's an interesting exercise to design questions. So can you give an example, like to illustrate this example? What? Illustrate this example. So when the results of several measurements will not coincide with either one of eigenstates. It's a challenging question.
Yeah, I'm not really sure.
Let's try to think constructively. Let's think. You'll take Josh. It's not you as an example, or maybe Adam. So suppose Adam has a mood to jump to another chair, to another seat, and we measure his position. So his position was like 2 meters from the wall, and when he jumps, it will be 4. So both of these distances are eigenstates because we are not supposed to sit between chairs. But if an abstract student decides to jump several times, and we will make a register notes where he right now, and then make an average. Then we will get a result that quantity D is sitting like 3 meters from the wall, right between the chairs, although he never was doing it. Does it make sense? It does. You believe it illustrates your equation?
Yeah.
Okay.
Can I give like the probability of finding it somewhere? Yeah.
So it's an average between other things. Any more questions to Joe? 1, 2, 3. No more questions. Let's thank Joe once again. So the next is Omolola Eniodunmo, and she allows us to call her Wyatt. Okay, we continue the story about observables and measurements.
Okay. Good morning, everyone. So I'll be speaking about the fifth postulate. The fifth postulate states that if you measure a particular quantity, say a physical quantity, and the result is AR, and that AR has a corresponding eigenfunction of phi r, then the state function immediately after measuring will still be phi r. Now, the basic idea of this postulate is a particle's position is unknown, and the only way we can know it is to measure it. However, by the time you make that measurement, the system will change. A measurement sort of like changes or disturbs the state of the system. So what do? At each point of measurement, you need to manipulate the system in a way that it goes back to the original state before making the next measurement. And this has to do with like the accuracy. So like for every time you make a measurement, you make sure that it goes back to the original state before making the next measurement. Applicability will be in the sense of the time-dependent Schrodinger's equation. As you can see, here, an example is me trying to measure the wave function right here. Now, for it to be able to return to this same state, it has to act on an operator, and you have to generate an eigenvalue right here, which is the time derivative. So it's returning back to the same state, but like there has to be an operation. It has to be operated on by an operator, and you're going to have to generate an eigenvalue. That's all. Thank you.
Okay, please join me in thanking Laura. Oh, anyone wanted to learn something from her right now? Any questions? Maybe when we do presentations next time, we'll set up preparing questions ahead of time, like distributing slides, and then you write down so you have time to think. But let's go to maybe one slide back, or even, yeah. So did anyone was surprised to see this statement? No, I was. I am every year. So if one tries to pursue this postulate in Wikipedia, it relates to collapse of wave function. And it means that measurement changes the wave function. It's one of the craziest things. So how do you interpret if you take an example of arbitrary student jumping between chairs? What the measurement would be? If like I like to jump between chairs and you measure me, how does it? What does it mean? Maybe making a photograph. On a photograph, it takes only one example, right? Taking cell phone and making photograph. Or I'm always trying to think, and let me try to draw something here. So if I'm not a physical chemist, but an entomologist, flower number 1, flower number 2, and there is a butterfly. It looks like quite angry butterfly. And this butterfly also jumps between flowers because it's nature. So maybe if I try to catch it, then I can report it was caught on the flower number 1, and its state can be changed. Make sense?
What do you mean by state can?
So state number 1, like state number 1 when the butterfly sits on flower number 1, state number 2 when butterfly is sitting on flower number 2. And if we measure, we catch it, it doesn't, we forbid it to jump. I'm not believing it's the best possible explanation, but at least it gets less conflict with common sense. So more questions to all. More questions one. More questions two. More questions three. Please join me in thanking all once again. And it looks like we did cover the measurements, and now we need to continue the thing that will start with those time dependence and then move to a little bit of mathematical background. So Nathanial, Aufman, yeah, floor is yours.
All right. My presentation is on postulate 6 of quantum mechanics. Postulate 6 states that the time variation of the state function is given by that equation right there, where H is the operator formed from the classical Hamiltonian system. And that equation is obviously the time-dependent Schrodinger equation. That's kind of what this whole postulate is saying. It's basically saying, hold, the Schrodinger equation is true. The time-dependent Schrodinger equation is the most general form, and it's used to describe a system that changes over time. There's many other forms. You adapt this equation to your needs of what the system requires. Little breakdown. H is the Hamiltonian operator. Psi is the wave function, whatever function you're using. T is time, and the H bar is Planck's constant. Thought I'd talk a little bit about the Hamiltonian more. A lot of you already did, but it is an operator that represents the total energy of the system. It's the sum of the kinetic energy operator and the potential energy operator. In classical mechanics, the total energy is potential energy plus kinetic energy. We just have to adapt it for quantum mechanics by taking the operator each. The Hamiltonian operator, you find it by replacing those classical observables with their respective operators. And we already saw this in one of the previous presentations, but it's just a table showing the observable and its representative operator. Maybe that's
Okay, please join me thanking Nate. Any questions? I have the one that I was already asking, so please just put it as a seed of thinking for the future. According to your time-dependent Schrodinger equation that you have introduced slide before, the psi wave function is changing over time.
Mm-hmm.
What are examples in which situations wave function does not change over time? And help from seeds is accepted.
Example where it doesn't change over time. Well, if you're just looking at one specific position of particle,
it could be distributed thing, distributed distribution. I'm excellent in language, which is an eigenstate of Hamiltonian. So if you make connection between time-dependent, time-independent Hamiltonian Schrodinger equation, if the wave function is eigenstate, not any arbitrary operator, but specific operator of total energy, then this state function will not change over time. And right now it is just verbal, but the rest of the course will provide support for this statement. So there, although Nate has introduced us time change of things, we will learn that sometimes things are not changing over time. More questions to Nate? If not, thank you once again. Are going to the mathematical backgrounds. So Josh, talk is yours, and we have 12 minutes for 3 talks. If you do it 4 minutes per talk, probably we will match your schedules.
All right, just testing. All right, can you hear me? All right, so my presentation it focuses on the sorry, it's just this thing is just getting away. Yeah, so focus on the vector rule, the determinant, and the inversion of a matrix. So the matrix by vector rule, you can form a matrix when you have a row vector, which is represented by a row of elements, and multiply by a column vector, which is like, as the name suggests, is a column of elements, and sometimes known as the outer product. So if you have like the column vector, I have an example here. So if vector A is 1, 2, and vector B is 1, 2, 3, in this case, both of them are row vectors. You want to make sure that one of them is a column vector, which in this case A, so that it has to transpose it or change it from row to column or column to row. And then you just multiply it. So in this case, you have the 1, 2, 3, and 2, 4, 6. However, you have the inner product, which is also known as the dot product. And when you do multiply two vectors, you get a scalar number. So in this case, the formula for in this case, a row vector of 2 elements and column vector of 2 elements would end up being AC plus BD, as seen in the red. You also have the cross product where you multiply 2 vectors to form another vector. So in this case, it's a bit more complicated. And usually, most of the time, like these vectors have like 3 elements which represent the x direction, the y, and z. All right, and then you have the determinant, which is a number that usually describes a matrix and can be used in like various formulas and equations, such as setting the linear change of area or volume. And if you notice, it actually looks a little similar to the cross product rule in that you end up having a difference between 2 products. The first one here is showing a 3 by 3 squared, so which means that you break it down into this last row and then multiply the determinants of the other part. Here, there's multiple ways showing a determinant. And so you can either have the DET, or you can have these lines that look for the absolute value, but they're not absolute value. And the bottom one is showing how you find the determinant of a 2 by 2 square. But to find the determinant, you need to make sure that you have a square matrix. And then you have the inversion. So you can only invert a matrix if its determinant is not 0. And also you can find the inverse of a matrix, and inverse of a matrix is also the same as the inverse of the product of all the other matrices. If the one matrix is the product of the other matrices. And to find this, you have this formula, and the inverse is usually represented by the -1 there. And here's just an extra website just for more information. And then if you multiply a square matrix and its inverse, you will end up with an identity matrix. And so here, usually the identity matrix represented by the capital letter I. On this case, I just have the subscript so that the 2 represents a 2 by 2 square matrix, and then a 3 is represented by 3 times 3 matrix. Any questions?
Okay, please join me. Thank you, Josh. Questions or comments? Question to Wyatt and to Josh. Why Wyatt used the word state function instead of wave function? And why you are presenting vectors and matrices instead of wave functions and operators. Any thoughts? So let me make a comment. It's a little tricky. So state function means it is a more global concept which includes both wave functions and vectors. And all abstract things that we were discussing today can be implemented, incarnated either as continuous functions or as vectors. Therefore, we are learning this matrices and we will use them through the course. More questions to Josh? If no, thank you once again. And Allison, for yours for another piece of linear algebra, a very practical one for finding eigenstates, which right now were introduced by previous speakers, right? So you have a proof that eigenstates are really needed in this course, and Allison will quickly overview things that probably all of us had in linear algebra, but it's important thing. And
all right, so I'm Allison, and I'm gonna confuse you guys a little bit. So I don't know about you guys, but when I'm learning information, I like to go to the background. So in 1829, well, the first one to publish this was Augustin Louis Cauchy. He stumbled upon the idea and what we call eigenvalues. It was initially called eigenvalues in Old English, but when time went on, it transferred into eigenvalues, which is German, meaning self. His research initially started with the unit circle, as his peers were looking for the explanation of the rotation of the planets. And his initial research was with the symmetry of matrices. That lovely guy up there is the reason why we're doing this. So to start off with, we've got the diagonalization of a matrix. So the basis of this lies on eigenvalues and eigenvectors to complete the transformation. So here's an example of what we could look for and what we can use diagonalization of. So you guys can get back to that. So some of the steps are to start with the equation ax equals lambda of x, and lambda is the number. You're going to subtract lambda x from each side to get that, and then you can factor out x to get the equation equal to 0, and that is identity matrix. And we're going to take the determinant of the matrix to find eigenvalues. Insert these numbers back into the diagonal with the zeros around, and you can find the final diagonal. And here's an example. I won't go through it all, but it starts off with the 3 by 3 matrix. And then we can see that we take the determinant of that, and then you can see at the end, it's kind of covered up, but we have the diagonal with the final one. So an eigenvalue is known as non-zero variable that is formed after a linear transformation. It's obviously always, most of the time, represented by lambda. As you can see, that is the equation. This is often a very confusing concept. I think our professor can agree. He would not like to solve these, but they're a little bit confusing. Here is an example of an eigenvector. It's a lot of work, but once you start to figure it out, it gets a little bit easier. Obviously, you can see that we start with a 3 by 3 again. Take the determinant in our equation, obviously, and we get down to the nitty-gritty, and then you can see our lovely answer at the end. So to simple it down, when you're looking at eigenvalue, it is referred to as set of scalar values, while the eigenvector is a vector in each direction of the linear transformation, which is what we're determining when we get our diagonal. So these values and vectors can help us simplify matrices and specific transformations, although they're sometimes confusing. But these are references and any questions.
okay, please join me in thanking Allison. Any questions or comments? Let me make a comment, not a question. So in the previous things, you have seen that one needs to find eigenstates of operators, right? So most typical, and I was asking question, when state function doesn't change over time. So when the operator or matrix correspond to total energy to Hamiltonian, and we found eigenstates as Allison taught us, then those states, which are eigenvectors of Hamiltonian, will not change over time as was shown in the time-dependent Schrodinger equation. Make sense? So it connects things together. More questions to Allison? If not, let's thank her once again. And now we have 1 minute for Adam to talk about evolution operator and connection to the time-dependent Schrodinger equation. His presentation is last but not least, and he makes a bridge to our next, to the whole semester, because the projects and next presentations will be related to evolution operator.
All right, the time evolution operator we get it from the Hamiltonian, because the Hamiltonian describes the total energy in the system, but that is directly related to time in a few ways. But the operator itself helps us predict states from a certain initial time into a future time t. So we can denote this time evolution operator as U. And it's a unitary operator, which means that it behaves a lot like matrices and that sort of thing. So if you multiply it by its inverse, you become, or it becomes the identity. Yeah, similarly, if we have two separate operators like A and B, it's important to note that the product AB may not be the same as BA. It's the commutator kind of is a way to check for this. So if that statement equals 0, then it commutes. It's just said to commute, which means that no matter which way that you apply these two different operators, you are yielding the same result. Yeah, that's much, but yeah, questions.
That's it. Perfect timing. Let's thank Adam for waiting for us to finish in time. And more, any questions? I think it's time. Yeah, thank you for completing. So it was a very successful session. Thank you for first for finishing it in time, and second for going over this complicated material. So in anything we will do later, we go more to applications, less mind drying abstract things. So have a nice weekend. No homework, because let's consider these presentations as a first midterm, because so you already got 25% of your final grade. So I think it will make you happy, and you will celebrate it over the weekend. So see you on Monday.
Thank you.